So the Gaussian distribution. So when you learn probability, I think typically what you do is you start with some distributions of random variables, and the Gaussian shows up pretty quickly, and it's a nice one. Here we just know why. We just know why we're going to be surrounded by the Gaussian distribution constantly. And the reason is because the Gaussian distribution is the thing that shows up as the limit of the central limit theorem as the minute you start talking about averages. And in stats, we talk a lot about averages. So that's where the Gaussian comes from, basically the central limit theorem. Now, the central limit theorem is actually quite impressive. It says that no matter what the distribution of your xi's is, as long as it has mean and variance, their average will, properly rescaled, go to a Gaussian. You could start with something nasty here, but this will go to a Gaussian. Okay, so this is like one of those beautiful old order of the universe type of results that says that if you take average of enough things, then it's going to go to a Gaussian. Okay, so the Gaussian distribution, you might know it under normal distribution sometimes. And this is basically showing up everywhere because of the CLT in statistics. It's named after Carl Friedrich Gauss, who's one of the most prolific mathematicians of the post-Greeks, I guess. And he actually introduced it in the context of statistics. So this guy was one of those broad mathematicians that studied, I think you go on his Wikipedia page, there's probably 15 topics that he was working on. And but he actually discovered this in the context of statistics, and then it went to have its own life in many other fields. And he was studying some astronomical properties, I believe, at the time. He's so famous that he was actually on the Deutschmark banknotes, well, until there was no Deutschmark anymore, I guess. So this is what it looks like. So the distribution x follows, so we write it as x follows n mu sigma squared. So you can see maybe some textbooks that you've seen parameterize this by sigma and not sigma squared. So you have to be very careful about this. Sometimes it changes. But in this class, the first parameter is always the expectation. And the second parameter that you see is always the variance. OK? And not the standard deviation. So if I say x is n 3, 6, then the standard deviation of x is square root of 6. OK? Most of the time, we'll work with notation, so you'll see sigma squared, and you won't have to bother too much. But when there's numerical examples, you have to remember which one this is. And software, for example, also have different conventions. So some software asks you to enter the standard deviation, and some software asks you to enter the variance as the second parameter. So be careful about that. OK, so this is a distribution. It's on the real line. It actually has a PDF. You've probably all seen it before. It's actually on this German banknote. Let's zoom in, and there you go. Here is the Gaussian distribution. And it looks like 1 over sigma square root 2 pi e to the minus x minus mu squared divided by 2 sigma squared. Trust me, I can read pixels. OK, so here's our Gaussian distribution. Sorry, let me just do this. And it has a lot of very interesting properties. So this is nice that the universe chose to have averages converge to the Gaussian and not something more nasty, because this one we can really play around with quite a bit. OK, so this is what the PDF looks like without the pixels. So it's indexed by, of course, mu and sigma squared. So every time you give me a different mu and a different sigma square, I'm going to get a different PDF. This is a family of distributions, not just one. So it looks like this. It doesn't really matter what the shape is. If you do enough statistics, this is something that you breathe. So this is the kind of stuff I know by heart. It's actually useful if you do calculus, that you know that this is actually a density because it integrates to 1. So if you want to cancel some terms in some complicated integration, you just make this appear, and it just goes away. So here are 2 examples when I took 2 sets of parameters, 0, 1, which is the so-called standard Gaussian, when the mean is 0, and the variance, and therefore the standard deviation, they're both equal to 1. So in this case, you get, this is the n01. So centered at 0, it's very symmetric. It has this so-called bell shape. And then when I start changing the mean, what I do is that I translate this thing. And when I change the variance, I actually make it flatter, right? So basically what I do is that I pull on the side so that it has more spread. But since the whole area under the curve is constrained to be 1, then what's happening is that the maximum value has to go down because I need to spread more mass farther. Okay, so I cannot aggregate it under this thing. That's what it looked like if I had an n minus 5 and standard deviation and variance 1/2. It would be something which is centered here and would be very spiky around here. Okay, so this is the family of Gaussians. The thing that's important about Gaussians, so Gaussians are everywhere, and you actually, even without the central limit theorem, people will use Gaussians in modeling assumptions where it makes no sense, right? This is the density. In particular, the exponential is never equal to 0, right? No matter what x I stuff in here, this number is never equal to 0. Which means that this thing allows for values that are infinitely large or infinitely small. Those things, everything's allowed. This is not a bounded random variable. I cannot use Hovding, for example. But I will use this to model heights. Okay, so this is actually if I collected a bunch of heights of students, and I said, what is the distribution of the height of a randomly selected student? I would say it's a Gaussian with some mean mu and some variance sigma squared that maybe I'm trying to estimate from data. Even though I know for a fact that nobody here has a height which is less than 0, for example. Okay? And so it's kind of a weird thing. You're using a random variable that allows for values that are very negative or very positive. Nobody here is probably 100 feet tall, but essentially you allow those things, but they never really come into play. And so this is exactly this property that we exploit here, is the fact that the tails, even though the exponential is never 0, the exponential can get really, really small. E to the minus 25 is really, really small, which means that this thing, for example, see how close those get to 0? Then the computer didn't even bother drawing them, right? They're right here. Between minus 3 and 3, everything's there. Beyond that, there's basically probability 0 of this happening. It's not 0, but it's certainly less than epsilon machine after a while. So essentially what you have is that those things decay exponentially fast. So in a way, you get the advantages of bounded random variables. They're actually almost in a bounded interval. And actually, if you look at Hovding's inequality, if I were to stuff in independent Gaussians there, you wouldn't even need Hovding because you actually know what the distribution of average of Gaussian random variable is. It's actually another Gaussian. Okay, so it's not, and you would be able to just look at the tails of the new Gaussian. So it's nice. Now, there's somehow it feels like this thing is, so I just tell you it's nice, but it has a complicated PDF. I want to model things that are finite, but I'm actually using something that have infinite tails. And now I'm going to tell you another thing that goes essentially, it sounds like it's going against. There's not even a closed form to compute probabilities. So when I want to compute the CDF, which I know is the first building block to compute probabilities by taking difference of evaluations of CDFs, then I'm actually not able to actually do this by hand. I cannot compute the integral I'm actually getting. So you're like, well, this Gaussian thing is kind of annoying. But we'll see that we actually, so those are the annoying analytical aspects of the Gaussian, but they actually, we recover them very nicely in other ways. Okay? So here, if I look at the CDF, which is just, remember the definition of the CDF is the probability that my Gaussian is less than little x, right? If I evaluate my CDF at point x. And so the way I'm going to do this is, well, all I know how to do is that it's the integral between minus infinity and x of my density in t dt. Okay? That's the definition. Turns out that's basically as far as I'm going to be able to get. Okay, so I could be an annoying calculus 1 teacher and say compute this integral and just like let you, stall like this. It's just actually not something you can come up with a number for. Okay? So computers do that for you. We'll see we'll use tables. So tables are this arcane way of computing this kind of thing. It's just that I'm going to use them for a very simple reason. I prefer you not to bring a laptop during a final exam for reasons that are quite obvious. So we use table as a surrogate for it. But in practice, nobody actually uses tables anymore.